I would like to introduce Un-Sun Lee. She's presenting her work on self-supervised domain adaptation for visual navigation with global map consistency. The work was presented this year at WACV conference, and we are very looking forward to the talk. So the stage is yours.
Hello, everyone. I'm Un-Sun from Seoul National University, and thank you for the great opportunity. I'd like to present our work, Self-Supervised Domain Adaptation for Visual Navigation with Global Map Consistency. So this was published at WACV 2022. So as it is very self-explanatory from the title, our work proposes a domain adaptation method for embodied agents to overcome the domain discrepancy between the noiseless simulator and the real world. Many embodied agents are generally pre-trained in a noiseless simulator with the ground truth labels, and due to the difficulty of collecting the ground truth labels in the real world. In our study, we assume that the dynamics noise, including the actuation and the odometry sensor noise, exists in the new realistic noisy environment. So we are trying to transfer the pre-trained agent, which was trained in the noiseless simulator, to the new environment where the dynamics noise exists. So we are suggesting a self-supervised domain adaptation method. Of course, it is self-supervised because the ground truth labels are not available in the real environment. And we're trying to close the sim-to-real gap for visual navigation agents. So we build our domain adaptation method on a map-based visual navigation agent. And we are employing the modular approach because the modular approach separates the observation space and the action space. As you can see, the observation space transfers the RGB observation and the odometry sensor readings to global maps and pose estimation, which are the domain agnostic intermediate representation. And in action space, given the global map and the pose estimation, the subsequent policy module then deduces the action for the embodied agent. So when the corrupted measurements, the actuation noise and the odometry sensor noise are given as input in the realistic environment or the real environment, it just suffices to fine-tune the observation module only to produce the stable intermediate representation. So if we can generate stable representation, which are the global map and pose estimation, then we can simply reuse the policy without any further adaptation when the pre-trained agent is deployed in the real world. So here we are formulating a self-supervised learning task where the agent is encouraged to generate consistent global map at different time steps. More specifically, let's say if our agent is generating a global map at time mt, then we are comparing it to the global map which is generated from the previous time step. So that's how we formulate this self-supervision loss. And to implement our self-supervision task more efficiently, we deliberately design overlapping trajectories by driving the embodied agent in round trips. So simply, we first navigate the agent in the new environment for a designated number of steps, and then we turn 180 degrees. And then we can drive the agent to execute the stored previous action sequence in reverse, then it simply generates the round trip. So, So the goal for this round trip is to make sure that the agent covers the same overlapping area during its forward path and the backward path. As I mentioned, in the new environment, we are assuming that the actuation noise exists. So it might not be possible to step on the exact waypoints that the agent stepped during its forward path when it's navigating its backward path. However, in our experiment, we verified that our suggested method still works in that situation. So during the forward path, the agent predicts the pose and it generates a reference map, MF. And then at the beginning of the backward path, we are resetting the map and it starts drawing a new global map. So even though we are resetting the map, the agent continues the incremental pose estimation, which has started from the beginning of the trajectory. So the same global coordinate is shared across all the maps, more specifically the reference map and the global maps generated after we reset the maps. So we incorporate the mean squared error loss to create a self-supervision signal by enforcing the consistency between the reference map and the newly generated global map. Because we're comparing the reference map to the global maps generated at every step during the backward path, it provides us a rich set of loss computations. So this loss formulation is based on the fact that we cannot assure that the reference map is error-free, but it is possible to assume that the pose error accumulates over time when the actuation, the odometry noise exists. So that tells us that the pose estimation incorporated in the reference map is more accurate. Reference map, or the map generated in the earlier step, is more accurate compared to the pose incorporated in the map generated in the later step, when the maps are generated within a single continuing trajectory. So in our paper, we are also suggesting a data augmentation method. We augment the trajectory data by enforcing the consistency loss on subsets of the original trajectory. As you can see, the original trajectory is utilizing the bisections of the trajectory. And on the right side, we are showing 4 different examples that could be augmented from the original trajectory. More specifically, we're augmenting the original trajectory by randomly sampling 3 different time steps in a chronological order. So the initial time T1, the turn time TO, and then the end time T2. And very similarly, the reference map is then generated from time T1 to TO, and then the reference map generated is compared to the every maps generated during from time TO to T2. So in our experiment, we are using the habitat simulator, and on the Gibson scenes, we implemented the domain adaptation method using PyTorch, and we are evaluating the agent's performance in 3 different metrics: localization, mapping, and exploration. And we evaluate on generalization and test time adaptation. So here's the qualitative result. As you can see, the first row is showing the mapping result, and the second row is showing the localization result. And the gray area is the ground truth map that could be generated from the simulator. And on the localization row, we are indicating the ground truth trajectory with red line, and all the blue colored map or the trajectories are the evaluated trajectory in the map. So we are comparing our model with 3 different baselines. First, no adaptation. It is the pre-trained model directly deployed in the new environment without any further adaptation. So this sets the lower bound of the performance so that we can compare our agent to it. And next, we are using domain randomization, which is the model pre-trained for the various combinations of noises with ground truth supervision, but in the training set. And lastly, GT supervised. We are using this GT supervised model, which is the model fine-tuned with the ground truth supervision in the new environment where the agent is adapted to. it sets the upper bound so that we can compare our model to. Finally, as you can see from the qualitative result, I believe that our agent better align with the ground truth than other baselines, except for the GT supervised model. But when we look at the result as shown in the table, our agent, it distinctively outperforms the two different baselines, no adaptation and domain randomization. And compared to the GT supervised model, it performs slightly worse than GT supervised, but our model still performs very well. In conclusion, in our paper, we are introducing a simple self-supervised task for robust visual navigation amidst actuation and odometry sensor noise. We are demonstrating that the suggested formulation enhances localization mapping in the final task performance. In our case, we are using exploration as the final task performance. And finally, in our paper, we show that the proposed method is applicable for test time adaptation. We believe that shows the potential applicability for real-world deployment. However, I did not include that in our presentation because due to the time constraint. This is the follow-up work. I'm presenting on Tuesday during the main conference session. I'll be presenting a poster for this paper called MODA, Map Style Transfer for Self-Supervised Domain Adaptation of Embodied Agents. The title is very similar, but just to shortly mention, compared to the work that I presented today, this paper suggests a self-supervised domain adaptation method which adapts for both visual noise and the dynamics noise. So please come by if you're interested. And thank you very much.
Yes, thank you for the great talk. If you have any questions for the speaker, feel free to raise your hands. If not, I have one question in the meanwhile. I am interested in the assumption on the round-trip behavior of the robot. So basically, I guess there's an assumption that the robot goes one way and then the other way back, basically to have some kind of loop closure. Like what happens if the robot in the domain adaptation in the real world deviates quite significantly from that part?
Okay, so well, to be honest, I think the main downside of this paper is to generating a round trip. So as I mentioned, our follow-up work is called MODA, and we are in that paper we are suggesting a method that's very similar, but we are not using the round trip, so that the robots deployed in the real world can still adapt with a similar method, even if the trajectory is not exactly the round trip. Yeah.
Okay. Are there any? Thank you. Are there any other questions? If not, I would like to thank the speaker again, and we would continue with the session.